Welcome everyone. So in this video lecture, we will study about free fall. What is free fall? What kind of characteristics we need to think about when we say an object is under free fall. So we will understand all that. Okay. Imagine that this is the ground and I throw a stone in the upward direction. So initially the velocity is going to be upward positive. Going to be in upward direction again away from the earth, and after some time the stone is going to take a U-turn because of the gravitation force, which we know is dependent upon the mass of the earth, mass of the stone, and the separation between earth and stone. And then stone is gonna come back and hit the ground. Okay. If gravitational force is the only force acting on the stone. Now this is important. If the gravitational force is the only force acting on the stone, then we would say this stone is under free fall. For free fall, only force acting on the object would be gravity or gravitational force. And this is important. So we don't want any other force on the object to be called an object in a free fall motion. We need to make sure that gravity is the only force acting on the object. Okay. Now, if gravitational force, let's say it is F, right? So that force is acting on the stone, which is pulling the stone towards the earth, right? So we know from the Newton's second law that force is equal to mass into acceleration, right? So the force formula from before will give us the force. If there is a force, there is an acceleration, right? So, and that acceleration would be in the direction of the force, right? So that acceleration would be downward direction. A different color here. So acceleration would be in the downward direction. Okay. Now, when there is a free fall and the only force acting on the stone or object is gravity, we actually use, instead of writing acceleration as A, we use the word G. Okay. And that is basically acceleration due to gravity. Okay. And just to make, just because of the gravity present, and that's what's causing the acceleration, so we call it G. Okay. And now we know that as the stone is actually moving, it has the force, gravitational force acting on the stone, which is pulling it downwards, and the acceleration because of that force is G. Okay. Now from the Newton's second law, we know force is equal to mass into acceleration, right? And that the acceleration here is gravity, right? So mass into gravity here. Okay. Now that mass is the mass of this stone. Okay. Now we also know from the gravitational force formula that force is equal to G m by d square. Okay. Now the small m is the mass of the stone. This big M is mass of this earth, because this is an earth, right? It's a big huge earth here. So that is the mass of the earth. And the D, so if this is an earth, I'm gonna draw something here just to give a idea. This is the earth, and it's like it's massive compared to stone, right? So the D is basically the separation between this to something different color here, center of the earth and center of the stone. So this is the D. Okay. So now both this force would be equal. Okay. So I can write G m capital M d square is equal to small m into G. And this is basically from equation 1 and equation 2. Okay. Now there are m present on both the side, so I can cancel the m out. So the G would be G capital G m by d square. Okay, now we will use some approximations here. Now we know that the radius of the earth is about, it's pretty big. I think it's on the order of like 10 to power 6 meter. It's huge. It's like, so it's like 1,000 kilometer, right? So that's the order of the earth's radius. Now if the object, if I'm throwing a stone upwards, it's not gonna go much far, right? So this distance, so I'm talking about the separation between the stone and the surface of the earth. Let's say that is a small distance, right? This value of the and the radius of the earth, let's say, is capital R. Okay, now so the d is basically equal to small r plus capital R, right? And based on the numbers we know, like, and our real life experience, we know this r would be much smaller compared to capital R, radius of the earth, right? So we can approximately say d is equal to r. Okay, now if you use that value, now just to be caution, like this is only true if your object is near the earth. Like if your stone, let's say, is at the moon or is at the sun, then this approximation will not be true, right? Then you have to actually use the real separation. Okay, but as long as you are looking at an object which are close to the surface of earth, you can approximate d by capital R. Okay, now so if I use that, then my small g becomes capital G, capital M, and then R square. Okay, now if you look at this, I'm gonna use a different page here. So I calculated that G is equal to capital G, capital M, and then R square. It's just amazing. If you look at it, all these values here are constant, right? So we know capital G is gravitation constant, which is 6.67 into 10 to power minus 11 Newton meter square and kg minus 2 here, right? Capital M, that is the mass of earth. Mass of earth is constant, right? So that would be something of the order of 6 into 10 to power 24 kg, right? And then R, which is radius of earth, is another value which is constant, and that is on the order of 6.4 into 10 to power 6 meter. You just look at this, all these variables to calculate the G is constant. Now if I put all these variables into this formula, the value G becomes 9.8 meter per second square. Okay, now that is just amazing, right? If you think about this, what it is telling me is any object, no matter how big or small, means if I'm throwing a 100 quintal of a stone upward or a small teeny tiny block of 1 gram, the value of the G on both the objects would be same. Not only that, every object which is near the surface of the earth has an if it is moving, it has an acceleration of 9.8 meter per second square. Okay, I want you guys just to remember that. It's like how we drive this value of the G. And don't forget the assumption. This is only true if your object is near the surface of earth. If your object is like on the sun, then the value of the separation cannot be approximated by just radius of the earth, right? And the value of the G would be different. Okay. Now another thing, means, one of the approximation we used is that separation between an object. So if this is my object and this is the earth, then the center of the object and center of the earth, I approximated that distance by capital R, which is the radius of the earth, right? Okay, now I want you guys to think that, like, as my objects are, as this separation or an object, so this small r, As this distance is getting bigger and bigger, the value of the g is going to change. And the value of the g is going to decrease actually if this small r is increasing. So if I have an object on, like, laying on the earth, okay, and then if an object is actually, let's say, on the Himalayas at the top, right, the gravity value would be slightly different, because the d, which is the separation between the object and the earth, is different. Even though the gravitational constant and mass of earth is constant, but the separation, the d value is different. d1, d2, right? So d2 is greater than d1. Then gravity acting on object 2 would be smaller than the gravity acting on object 1. Now, as long as the separation, this object doesn't go very far off from the earth, that difference, this is not going to be huge. So you can approximate by 9.8 meter per second square. But if your separation starts going really, really big, then you need to think about it. Okay. I hope that gives you an idea about free fall, what we call free fall, and how we calculate the acceleration in the free fall. Okay. In the next lecture, we will study about the motion of the objects in the when they are under gravitational force.